Okay, here's your review for test number 3. First off, we want to know how to graph exponential functions, and I know the directions here say, um, graph the function by making a table. We really shouldn't have to make a table, but let's say we did. We pick an x, we get an f of x. So let's pick, I don't know, -1, 0, 1, 2, 3. And so you're going to plug these in here, so you have to do 2 to the -1, 2 to the 0, 2 to the first, 2 to the second, 2 to the third. And so 2 to the -1 is 1 over 2, 2 to the 0 is 1, 2 to the first is 2, 2 to the second is 4, 2 to the third is 8. And so these would be your y values, 1/2, 1, 2, 4, 8. And so you plot these points, connect the dots, but you should know that the graph of something like this, because the base is 2, should look like that. So that's your basic exponential function where your base is bigger than 1. It should have that increasing shape. What do we have? We have a horizontal asymptote down this end. Okay, we go through this point right here, which is 0, 1, found right there in our table. And then we could obviously plot all our other points, and we would see we would get this shape. So now we want to take that and adjust it. So we're going to use that graph of 2 to the x, and we're going to use that so we can graph 2 to the x minus 1. Notice this minus 1 is up in the exponent, and so that's the inside of the function. And so in that case, if we're subtracting 1 from inside the function, we're going to move to the right 1 unit. And so if we take our basic graph, which looked like this, went through this point 0, 1, and we move that to the right 1 unit, okay, let's change our color, we would be now at this point, which would be at 1, 1, okay, so that's that point 1, 1, and then the graph would follow suit with that, and would look like that final picture. Here we want to use the graph of e to the x to draw e to the x plus 3. Notice this plus 3 is not in the exponent, so in which case that's going to move it up 3 units. And so I'm going to take my basic e to the x, which looks a lot like 2 to the x, so it looks like this. Okay, goes through this point 0, 1, has this horizontal asymptote. I'm going to take all that and I'm going to move it up 3 units. So everything's going up 3 units. And so what does that do? Well, what that does is it puts my horizontal asymptote all the way up here at 3. That's a y value of 3. It puts this point up 3 units. It puts it up here at this point 0, 4. And then my graph follows suit with that and then looks like this. So again, horizontal asymptote. That horizontal asymptote's at y equals 3. At this point 0, 4. And I'm going to go through. My graph's going to follow that trajectory. So here we want the accumulated value of compound interest, okay? So we have this formula that says P times 1 plus R over N to the NT would be a compound interest formula. P is the investment, that's the $17,000. R is my rate, that's the 6%, 0.06. N is the number of times we're compounded, and T is the number of years. Okay, so 13 years. So compounded, well, it's compounded annually, which means once a year, so N would be once. So if I plug all that in, A equals 17,000 times 1 plus 0.06 over 1 to the 1 times 13. That'll give me my answer. So I came up with an answer of $36,259.78. Similar question, different amount of money, different percentage, and compounded differently. So if we use that, A equals P times 1 plus R over N to the NT, this is now going to be 900. R is 12%, so 0.12. T is 2 years. Remember, T is always measured in years. Okay, and then N here and here is compounded rate. So quarterly, so N would be 4. So we're going to get 900 times 1 plus 0.12 divided by 4 to the 4 times 2. So I ended up with $1,140.09. One money percent compounded years. So A equals 1710 times 1 plus 0.06 annually is once to the 1 times 12, and that'll give you your answer. Now that's not that different from the first one, so just different percentages, so we should be able to get that answer. Now what if, now again, we can get that answer. I'm going to get 17,000 times 1.06 to the 12th. And I end up with 34,207.34. Now what if I change this and I said compounded continuously? Well, what does that mean? What that basically means is that n is infinite. So the number of times it's going to be compounded per year is an infinite amount of times. We have to change our formula. The second is compounded continuously versus annually, monthly, quarterly, etc. We now use this formula, in which case n has already been figured in, because you can't plug infinity into your calculator as a value to plug into a formula, and so essentially it's already been figured here with this formula. Notice there's no n anymore, and so we would just use the principal, we would use E, and then the rate, the rate was 6%, and the years was 12, and that would give us that continuously compounded. Now this would also be the maximum amount, because the more you compound, the more money you get. Well, we can't get any more than an infinite, so this would be the maximum we can get. You would plug that into your calculator, and also this number's wrong. I was going off of 17,000, not 1,700. So I'll rework that as well. But anyway, let's go back down to this one. So 1710 times E to the 0.06 times 12. So here I got 3,513.08. Okay, now let's go back up and rework this number. I used 17,000 here, not 1,700. So let's go back 1710 times 1.06 to the 12th. Let's try that again. 1710 times. So this should have been $3,440.86. Okay. If this was $17,000, then we would have gotten a $34,000 number, but that was kind of ridiculous. So 1,700, and we get this number, which is less than this, because why? We're compounding it once a year versus infinitely many times a year. And so this would be the maximum amount. But I just wanted to change the problem in case you see continuously compounded, you know it's a slightly different formula where n has already been figured in. We want to start working these log expressions and understand how they work. So let's start with a log base 3 of 27. So we want to figure out what the answer to this is. Well, remember, these are basically written in terms of exponentials. 3 is my base. I don't know what the exponent is, but I know the answer was 27. That's how you read this. 3 to some power gives me 27. The second you see that, you understand that the answer should have been 3. 3 to the third power is 27. You go to the next one, log base 10 of 10,000. Okay. Now, they don't necessarily have to write this base here. If they just wrote log of 10,000, okay, it would be the same thing. But what are they asking? 10 to some power equals 10,000. And so you basically can do it by counting the number of zeros. Well, 10,000 has 1, 2, 3, 4 zeros. And so the answer would be 4. 10 to the fourth, right? 10 to the second is 100, 10 to the third is 1,000, and 10 to the fourth would be 10,000. Okay. All right. And finally, log base 5 of 1 over 25. Oh, 1 over 25. That's messy. Let's clean this up. 25. Okay, so again, 5 to some power gives me 1 over 25. Again, I know 5 to the second gives me 25, but I want to kick it down to the denominator, so that has to be negative 2, right? Because 5 to the negative 2 is the same thing as 1 over 5 to the positive 2, and then that would give me 1 over 25. So there's my answer. So first one, the answer is 3. Second one, the answer is 4. Third one, the answer is negative 2. So understanding logs is all about understanding its relationship to exponential functions. Here we want to get back into graphing. In this case now for logs, we want to use the log base 4 of x to help us graph log base 4 of x minus 1. Now notice this minus 1, there's a difference if it had parentheses around it or not. In this case, it did not. If it had parentheses in it, the x minus 1 would be inside the logarithm, but it doesn't have parentheses. So that minus 1 is outside the logarithm. So if you're outside the logarithm, that's going to move it down 1 unit. Well, you got to remember, what does this look like? So if I was to graph a basic log base 4, being that that base is bigger than 1, it would start off looking like that. Okay. It would have a vertical asymptote here at the y-axis. It would go through this point 1, 0, and would have this increasing shape. So here's your x-axis, here's your f of x-axis. Okay. But now I want to take that whole thing and I want to say minus 1. So that means go down 1 unit. So if I'm going to redraw that, I go, okay, well, if I want to slide this thing down 1 unit, the vertical asymptote is still going to be the y-axis. Okay, this point's going to go down 1 unit, so that's going to put me here at negative 1. So 1, negative 1 would be that point, and then everything else would kind of slide along with that, and it would look like this. So 1, negative 1 would be the point. Have the vertical asymptote still at the y-axis, and you'd have your increasing shape. I want all this detail in a graph. So when we switched it to log base 5 instead of log base 4, it doesn't really make a huge difference. It's a base bigger than 1, so it's not going to change the shape very much. But this is the big thing. Look, that minus 1 is inside the parentheses. Well, if it's inside the parentheses, that means I'm going to move to the right 1 unit versus down. So if I took, again, my initial log base 5, which is going to look like this, okay? So it goes through this point 1, 0, has this vertical asymptote here at the y-axis, right? And then I redraw that, but I'm going to go to the right 1 unit. Well, everything's going to the right 1 unit, which puts my vertical asymptote now at x equals 1. Okay? And then this point goes over 1 unit, which now puts it here at 2, 0. And then my graph follows along with that. It looks like this. It should go like that. And that's the graph of that logarithm. So I have my point, I have my asymptote, I have my shape. Those are all the things I'd be looking for. Okay, then here we switch it up to a natural log. All we're doing is changing the base. So we're saying the base is e, but e is a number bigger than 1, so it really isn't going to look that different than the base 4 or the base 5 logarithm, which means it's going to start off looking just like this. And so it's going to go through that point 1, 0. It's going to have the vertical asymptote at the y-axis. And now we're going to do a little bit more to it. So we have two things. We have this negative here, and we have the plus 3. So the negative multiplied on the outside, that's going to reflect it. Okay, so which way is it going to reflect it? That's going to reflect it over the x-axis. It's going to flip it this way. Okay, so flip over x. And then plus 3, that's not in parentheses, so that means it's outside. That's going to go up 3 units. So if I were to flip this graph over the x-axis, it would look like this. Okay, This comes down here, this goes up here, so it would have this shape to it. Okay, still going through the same point, but now the vertical asymptote's up here on this end. Then I'm going to move that whole thing up 3 units. So let's put that all together. So this point is going to go up 3 units. 1, 2, 3. It's going to be here. So it's at 1, 3. Again, we're going to have that upside down shape to it like that because it got flipped. And so this is 1, 3. It's got this vertical asymptote here at the y-axis and has this other shape flipped over. All right, here we want to use our properties of expansion. So remember there were 3 properties of expansion. Log of a product turns into sum of logs. That's U, that's V. So if you have multiplication inside, add 2 logs. We have division inside. It turns into the subtraction of logs. And if we have something raised to a power inside our logarithm, that power comes out to the front as a multiple times the log. Okay, so multiplication to addition, division to subtraction, powers come out the front as a multiple. So let's look at this one here. So first off, we have multiplication, y times z to the 6th. So I'll write that as log base b of y plus log base b of z to the 6th. Now there's not much else we can do in the first one, but here the z to the 6th, that 6 can come out. So I can write this as log base b of y plus 6 log base b of z. Okay. How about the next one? Well, let's start with this division. Log base b of xy to the 4th minus log base b of z to the 6th. Now individually this is multiplication, so I can expand that. Log base b of x plus log base b of y to the 4th minus log base b of z to the 6th. Now this power can come in front of that one, this power can come in front of that one. So I end up with log base b of x plus 4 log base b of y minus 6 log base b of z. All right, so here's 2 equations we want to solve. They're exponential equations, so I have 4 to the x plus 7 equals 5. And so the key to solve for x is to get rid of the 4. We want to get the exponential by itself first. It already is. So if I do log base 4 of 4 to the x plus 7, then I have to do that on the other side. Okay, that allows these to cancel, giving me x plus 7 equals log base 4 of 5. And therefore x equals log base 4 of 5 minus 7. So that would be your answer, and you could leave your answer like that. But if you want to plug that in your calculator, you can't plug this in your calculator. So maybe you want to write your answer in terms of natural logs, in which case you can say the natural log of 5 over the natural log of 4. So use the change of base formula to convert this to natural logs. So take the log of this divided by the log of this, minus 7. And then you can plug it into your calculator and figure out what the answer would be from there. But that's writing the answer in logs, and the purpose would be so that we could calculate the value of that in our calculator. Okay, so if we want to do the other one, e to the 2x equals 7, again, you want to get the exponential by itself, it is. Now you want to get rid of this e. Well, you do it with a log. What log? Same base, so we have 4, 4. Base e is natural log, so natural log of e to the 2x equals natural log of 7. These cancel, so 2x equals natural log of 7 divided by 2. So x equals the natural log of 7 all over 2. Now that one's already in terms of logs, and you could directly plug that into your calculator, but that's a fine answer. You could leave your answer like that. Okay, so now we have 2 log equations. Again, the key is to get the function by itself. So we already have the log by itself. So you want to use e to get rid of the log instead of the log to get rid of e. So we take e to the log x. And if we did that on one side, you have to do e to the fourth. So basically put both of these up in the exponent for base e. These cancel. X equals e to the fourth. Done. Now this one we want to get the log by itself first. So I would divide by 2 and have natural log of 7x equals 9. Now basically do the same thing. E to the natural log of 7x equals e to the ninth. These cancel. 7x equals e to the ninth. Divide by 7. X equals e to the ninth over 7. There's your answer. Okay, on this one, we need to do a little bit more work. And so we have to put this as one logarithm. Remember, we want to get the log by itself, but there's two logs. Luckily, they're the same base, and they're added together. So we saw properties of logs where addition came from multiplication. So I could put this together as log base 3 of x minus 2 times x minus 8 equals 3. Then I can get rid of the log by doing 3 to the log base 3 of x minus 2 times x minus 8 equals 3 to the third. Cancel. So now we have x minus 2 times x minus 8 equals 27. Now to solve the resulting equation, because we have these two parentheses with x in them, we have to multiply this out. And so I get x squared. I'd have a minus 2x and a minus 8x, which gives me minus 10x. And then I'd have a plus 16 equals 27. So it's a quadratic equation, so I'll set it equal to 0. So subtract to 27. If I subtract to 27, I'm going to get 11. Minus 11, sorry. And so if I were to factor this, I would have x minus 11 times x plus 1, giving me x equals 11 or x equals negative 1. Now, one thing we have to understand, and we didn't do it in the previous problems because it didn't need to be done, but we really should do it with every problem that has a log in it, is we should check our answers. We want to make sure that when we plug these in here and here, that we'll be able to do these logarithms. So remember, logarithms, you can only take the log of a positive value. So if I plug 11 in here and I don't get a positive, then I can't do these logs and therefore it can't be a solution. But if I plug 11 in here and here, I'm going to get 11 minus 2 and 11 minus 8. Great, both times positive, so that's going to work out. But if I plug negative 1 in here and here, negative 1 minus 2, that's negative. Negative 1 minus 8, that's negative. Just one of them is a problem, but I can't do this. Log base 3 of negative 1 minus 2, which is log base 3 of negative 3. You can't do this because you cannot take the log of a negative, because 3 to some power will never. Sorry, a little technical difficulty, but so if this equation, if we have two solutions, x equals 11 and x equals negative 1, the only solution can be 11 and not negative 1. So therefore, we could just circle the ones that work, cross out the ones that don't work, but understand that this does not have two solutions. It only has one solution. All right, so in this question, we have an example of a future value problem. And so Bill needs $8,000 to buy a new car in 5 years. So he wants the future value to be $8,000. He has 5 years to get there. How much should he deposit at the end of each quarter into an account that earns 8% interest, compounded quarterly, so that he can get that $8,000 in the future? So we have this future value formula. So future value equals P times 1 plus r to the n minus 1 divided by r. But we know the future value. We're trying to find how much he needs to pay into the account each quarter. And so we have to resolve this formula. So if you resolve the formula, multiply this r to the other side, divide by this, 1 plus r to the n minus 1. That'll give you your payment. And so in this case, we have our future value to be 8,000. We want to do this in 5 years, so we need our rate and we need our number of pay periods. Well, our rate is 8%, but that's compounded quarterly, so we have to take that 8% and divide it by 4. That way, each pay period will know that it's 8% divided by 4, since it's split up 4 times a year. And then for 5 years, how many pay periods are we going to have? Well, it's 4 times a year for 5 years, 20 total pay periods. Okay, so if we plug all this into this formula, we're going to have 8,000 times 0.08 divided by 4 over 1 plus 0.08 divided by 4 to the 20th minus 1. Put all that in your denominator. That'll give you your pay period, your payment. So put this in your calculator. You clearly see that your payment each month that you have to save up is going to be $329.25. So if you put $329.25 into your account every quarter, and 5 years, you're going to get $8,000 total. So that'll be your future value of $8,000. This will be the payment you need. In this problem, we're going to present value of an annuity. We're looking for what the present value needs to be, or would be, if we have $150 per month for 3 years at an interest rate compounded monthly. And so your present value formula would be P times 1 minus 1 plus R to the negative N all over R. And there's no resolving this formula. We were trying to find the present value. Okay, so we have our $150 a month. Okay, 1 minus 1 plus R. R is 3%, but that's compounded monthly, so we'll divide that by 12. To the negative N, well, N is the number of pay periods. Well, if it's 3 years and it's monthly for 3 years, that'll be 12 times 3, so 36 would be your number of compoundings over the course of this period. And then you divide by R again, which is 0.03 divided by 12. Okay, so plug all that in your calculator, and you're going to come up with $5,157.97. And that would be the present value. So you would need to start with this amount so that you can get paid $150 per month for 3 years if you're working at a 3% interest rate compounded monthly. And so now, final question. If you deposit $2,000 into a fund that pays 4% interest compounded monthly, how much can you withdraw at the end of each month for 1 year? And so trying to figure out what this is. Well, essentially saying this is your starting amount. That's your present value. This is your interest rate. You're then going to try and pay yourself a certain amount each month. Okay? And the question is, how much could you pay yourself at the end of each month for a full year if you started at that amount? So this is a present value formula. So we have our present value equals P times 1 plus, 1 minus 1 plus R to the negative N all over R. And so if we plug this in, we're going to say, all right, well, we're looking for how much we could pay ourselves. Okay, what's our payment going to be? So we have to resolve this, and we have P present value times the rate. So multiply this to the other side, then divide by this whole thing here. You have 1 minus 1 plus R to the negative N, and that'll tell us what our payment is. And so we started off with $2,000. That's our present value. Our rate is 4%. But again, that 4% is compounded monthly, so we'll divide that by 12. Then we have 1 minus 1 plus, again, 0.04 divided by 12 to the negative N. Well, what's N? N is the number of pay periods. Well, you're doing it every month for a full year, so 12 total pay periods. And so if you plug this into your calculator, that'll tell you what you could pay yourself each month. Well, if you plug this in your calculator, you're going to find that you get $170.30. So if you start with $2,000 and you put it into a fund that earns 4% interest, you could pay yourself $170 each month for a full year out of that starting amount.